Started. Please continue.
So let me introduce my lab, Innovative Design Optimization Lab, in short, IDO. So this is my picture. And I graduated Seoul National University in Korea, and I moved to US University of Iowa. My advisor is KK Choi. And these are the research area I'm focusing on right now. So reliability-based design optimization, Rbdo, and also surrogate model generation and optimization. And design under uncertainties or multidisciplinary design optimization, topology optimization, and finally, artificial intelligence, so AI-based design optimization. And I saw from the flyer, surrogate model and this topology optimizations are also included in this workshop. And I have many students. So if you have any question, you can contact me using this email address. So today, like I told you, we will focus on reliability-based design optimization. And this is my research overview, which covers everything that I carrying out right now. So Rbdo, reliability-based design optimization, is actually a design optimization under uncertainty. So since there exists uncertainty in the real world, we have to perform design optimization considering this uncertainty. So Rbdo is one way of considering design optimization under uncertainty. So Rbdo or CBDO and so on. So this is the main focus of my research area. But in many cases, we may not have a cheap computation or computational model. In that case, we can use surrogate modeling. So I also studying this surrogate modeling methodology, which includes single fidelity or multi-fidelity surrogate modeling or AI-based surrogate modeling and so on. So these two are actually my major research area topics. And sometimes surrogate modeling or computer simulation could be biased from a real experiment. So in that case, we may have to perform statistical model calibration. So which means experiment and the simulation could be different. Then we have to adjust this simulation model so that this simulation model mimics this experimental result very well. And then also this is a structural optimization application, which uses a topology optimization. So I newly designed a ship engine or engine basement. Also, I performed AI-based design optimization. But basically, we will focus on this design under uncertainty today. Then this overviews Rbdo process. So when we perform Rbdo, we need these four steps. So first step is input estimation. So since we know inputs are uncertain, then we have to model this uncertainty using statistics or probability theory. So here PDF is majorly used to model this input uncertainty. So probability density function. So it could be joined, correlated, or it could be independent. Anyway, we need to model input this statistical model. So if this input is ready, then we have to use this information in model estimation process. So for modeling, we can use real experiment, which is very expensive, or simulation model. So some simulation model is also very computationally expensive. In that case, we can use surrogate model. So once model is ready, then using this model, we will perform analysis. So here, analysis means reliability analysis in Rbdo. So we have to evaluate this reliability. So that's actually the purpose of reliability analysis and Rbdo. And the reliability is defined like this. So probability, PR means probability that certain performance is greater than this given target value. So this is a reliability. And then this probability can be expressed as a multidimensional integration using joint PDF, which is obtained from this first step. But this is not easy to obtain mathematically, so we have to have some assumption, to approximate this reliability. Or if this sign is opposite, then that is called probability of failure. So to obtain the probability of failure is the purpose of reliability analysis. So we need this kind of input model. And once reliability analysis is done, then we can perform optimization, Rbdo. So the purpose of Rbdo is to reduce or to increase reliability. So here, this is original design. Then if this is a target, then this much failure we may have. Then that means reliability is relatively small. Then by changing design, we could obtain this optimized design where failure is much smaller than the previous design. So to obtain this kind of reliable system design is the purpose of Rbdo. So we will study this step one by one in more detail. And before we jump into Rbdo, let's briefly see the motivation of Rbdo. Yeah, so for the motivation, let's first use a one-dimensional cantilever beam. So here, when I say one dimension, then the dimension means number of design variable or number of random variable. So in this case, design variable is just one. So it is called one-dimensional cantilever beam. So usually, deterministic design optimization is formulated like this. So optimization formulation. So in this case, it is not probabilistic. So it is called deterministic design optimization. So we want to usually minimize volume of this beam. And subject to, so which means constraint is maximum stress in this beam should be less than or at least equal to allowable stress. So here maximum stress occurs at the root of this beam. And for this simple rectangular beam, we know how to evaluate this maximum stress using solid mechanics knowledge. So we can express volume using this parameter or a variable. So W times L times H. And the maximum stress which occurs here also expressed like this. So for the optimization, we have cost function, which is volume must be minimized, and constraint. In this case, maximum stress. So cost and constraints are available, and also we need to define design variable. So design variable is the height of the beam. So there is only one design variable, H. That means others, L, P, W are parameter, design parameters in this formulation. So design parameter means actually in this case, this is constant for deterministic design optimization. So this is called one-dimensional design optimization since there is only one design variable. And also this is called deterministic design optimization because this variable H is deterministic, not random. Since objective function and constraint functions are analytically obtained like this, we could draw these functions. So volume is, in terms of H, design variable H, volume is a linear function. So it is increasing like this as H increases. And maximum stress, which is a function of H also, is decreasing because it is proportional to 1 over H squared. So it is decreasing like this. And allowable stress is given. So this is target value. Then to satisfy maximum stress is less than allowable stress. Then we can select this to minimize volume at the point. So this is optimum design for this one-dimensional cantilever beam optimization problem. However, due to manufacturing process, this H or W or L may not be deterministic. So even if we say H is like 1 centimeter. If we actually manufacture this beam, then the actual height could be different from 1. So it could be larger than a target value, or it could be smaller than the target value. If the actual height is smaller than this target value, then that means stress at the point is larger than the allowable stress. So that means that design is failed. So in actual case, what if this parameter or variables follow a certain distribution? Then if we assume this h height follows a normal distribution like this, then this variable is called random variable. So random variable means we can define that kind of variable. It follows a distribution. So if we describe a certain variable which has a distribution, then that variable is called random variable. So here we have only one design variable h, and it follows this kind of normal distribution. Then that means if we make infinitely many this kind of one-dimensional cantilever beam, then 50% will be failure and 50% will be a success. Then in this case, this design has 50% failure and 50% reliability. So reliability of this product will be 50. So this is actually a motivation of Rbdo. So then reliability-based design optimization, Rbdo is necessary to satisfy certain level of product reliability. 50% may not be enough for a reliability of this kind of product. So what if we increase this reliability to like 95% or 99%? Then how we can perform design optimization under that target? So that's the purpose of Rbdo. So for that purpose, it is very important to accurately and efficiently estimate the reliability of products for Rbdo. So efficiently means we want to minimize computation to obtain reliability, and accurately means since we are introducing some assumptions for reliability estimation, so we want to minimize that kind of error in estimating reliability. Yeah, so to apply Rbdo concept in this one-dimensional cantilever beam, so that means here, this is the current design. Then to minimize or to reduce this failure, we know we have to shift this design to the right. So that means we have to increase the height of the beam so that the failure is reduced. So in Rbdo formulation, still we want to minimize volume. So in this case, volume is not a function of h itself because h is a random variable, so we cannot directly use h as a function. Instead, we use mean value of h as a design variable. So in Rbdo, mean of the random variable is used as a design variable. And constraint, now it is changed. So previously, constraint was maximum stress should be less than allowable stress. But in Rbdo, the probability that maximum stress is greater than allowable stress, which means this is actually a failure. So probability of failure must be less than or at least equal to target probability of failure, and the customer will give this target probability of failure like 1% or 0.1% like that. Then to obtain a probability of failure, we have to obtain this. And since this is a one-dimensional problem, it is very easy because we don't need to perform multi-dimensional integration. We can only perform one-dimensional integral. Then that means integral from -infinity to this point, h star of joint PDF of input variable h. Then actually this is same as CDF, cumulative distribution function of design variable h evaluated at h star. So it is important to find this point. Once we find this point, then integral from negative infinity to up to this point can be easily obtained using this function in one-dimensional case. So this is just limited in one-dimensional case. If it is high-dimensional case, the equality sign becomes approximation, and we may need to introduce another mathematical trick. So it is important to find this point H star, and this point is called most probable point. So in reliability analysis, it is very important how to find this most probable point MPP efficiently and accurately. And like I told you, we need a probability density function, which is obtained from input estimation, or in many cases, we just assume this is given or available. Usually we use normal distribution or Gaussian distribution. Then once we obtain this probability of failure, then reliability is defined as 1 minus probability of failure. So reliability analysis means obtaining probability of failure. So this is a one-dimensional example. So we can easily obtain one-dimensional problem and analytical problem. So we can easily obtain that. But for general application, so we have to generalize this process. So for that purpose, first we need to introduce Rosenblatt transformation in reliability analysis. So Rosenblatt transformation means in the original design space, X space, the design variable H can follow any distribution, but for performing reliability analysis, we have to have standard normal U space. So we have to transform this X space to U space using Rosenblatt transformation. Then in this space, U space, all the random variables follow standard normal distribution or standard Gaussian distribution. So standard normal means mean value is always 0 and the standard deviation is always 1 in the space. So Rosenblatt transformation can be obtained using CDF. So CDF of original random variable H and CDF of standard normal variable U. So using this transformation, H can be easily obtained like this. So plugging this H into the original equation, then volume and the constraint can be expressed as a function of U. Then we can transform this original space to U space. And also, it is important to measure the distance from the origin to the this MPP, most probable point, in the standard normal space, because this distance defines reliability. So distance from the origin to the MPP in U space is called reliability index and usually denoted as beta. And if beta is 3, then that means in the standard normal U space, standard deviation is always 1. So beta is equal to 3, meaning it is 3 sigma design. So here, to denote the standard deviation, we use sigma. I think you heard of 6 sigma design, and then the 6 sigma. The sigma means standard deviation. And the probability of failure is calculated like this capital Phi of minus beta in standard normal space. So which means once we know how to obtain beta, we can approximate the probability of failure. And this is actually exact in this one-dimensional space. And this process is called reliability analysis. And in more specific way, it is called MPP-based reliability analysis. Since we are also studying sampling-based reliability analysis, and the sampling-based reliability analysis doesn't require this kind of MPP search. So we will study both MPP-based reliability analysis and sampling-based reliability analysis today. And this is also another motivation, because why we need to study reliability-based design optimization? Because uncertainty exists everywhere. So here, this figure shows uncertainty exists everywhere. So this means load and wind load, and this is wave. So they are all uncertain. So we have to use some kind of distribution to model, statistically model the wind load. So wind speed is different every time. And also material property, hardness or yield strength are uncertain like this. So whenever we test, we can see different yield strength or fatigue life or hardness. Also, like shown before, dimension of the product is also uncertain. So even if we have a target dimension, when we actually manufacture the product, the actual dimension could be different from target. Then we may have to use random variable to describe the dimension. So because of this kind of uncertainty existing everywhere, we have to consider these uncertainties to guarantee the target of reliability. So this is just an enlarged figure from the previous slide. So fatigue strength coefficient and exponent, and the fatigue ductility coefficient and exponent. They are uncertain, so which means each coefficient or exponent follows certain distribution, and also they are two random parameter are correlated. So which means one increases, the other decreases. So one increases, the other decreases. So they are correlated to each other. So this is actual data, 29 data from this material, SAE 950X steel. So we can see it is scalar and highly and negatively correlated. So we have to consider this correlation as well to obtain accurate reliability estimation. And this slide shows even if we don't consider correlation, the result could be different. So here we are dealing with the same fatigue material result. And here, this slide shows if we don't consider this material property correlation, then the actual data, which is a red dot, is different from simulation result, which is gray line. But if we consider this material property correlation, then this gray line and the red dot are matching each other. So we have to consider this correlation as well. So in summary, we have to consider this statistical input property to accurately perform reliability analysis. Then this is a comparison between safety factor approach and the reliability-based approach. So safety factor approach is a widely used design approach. And reliability is a relatively new design approach. And to guarantee this kind of reliability, a safety factor approach introduces a safety factor or safety margin. So this safety factor approach is deterministic design approach, and it introduces a safety factor or safety margin to guarantee a reliable design. However, the main problem of this approach is safety factor is obtained through experience. So from experience, we can say we could use safety factor of 3 for the design of this product. But if we have to design a new one, then since we don't have any experience, we may not have any accurate safety factor estimation. In that case, we cannot accurately estimate the reliability of the product. And actually, this safety factor is not mathematically obtained. It is obtained by experience. So it doesn't guarantee the reliability, target reliability of the product. However, in reliability-based approach, we are using probabilistic design approach, and then reliability analysis is required. And if this reliability analysis result is accurate, then we can guarantee reliability of the product. So target reliability is used to guarantee reliable design, and this reliability is obtained from probability. Oops. Sorry. Yeah. obtained from probability theory. So which means mathematically we can obtain this reliability, not from experience. So this is more advanced, mathematically advanced approach. So since we overviewed the motivation of Rbdo, so let's move to reliability analysis. So concept of reliability analysis. So let's consider this kind of simple shaft example. So when a performance function, reaches a certain threshold. So here performance it could be stress or fatigue life or any other mechanical performances. So if a performance reaches a certain threshold, then the state of the component or system will change from safety to failure. Then this threshold is called limit state. And if we use a threshold of 0 as a limit state, that means g of x. So g means performance function. So g of x is equal to 0 divides the random variable space into safe and failure region. And in this slide, we will define failure like this. So if performance function, when we use 0 as a limit state, if performance function is greater than 0, the product is considered as unsafe or a failure. So if that's the case, gx is equal to 0 is called the limit state function. So here, 0 is limit state, and this is a performance function, and the limit state function divides into two regions, safe region and the failure region. So in this case, shaft design problem case, we can use this maximum equivalent stress as a performance function. Then this stress is expressed as a function of design parameter. Then the failure will be given like this. So this evaluated stress is larger than yield strength. Then this will be a failure. Then to have 0 limit state, we could move S to the right. Then SE minus S will be limit state function. So here SE is given like this, and the minus S is equal to 0. So this is a limit state, and this is limit state function. So for the reliability analysis, we will use limit state function. So here in the figure, this red line is limit state function, and this red dot means given design. So like I told you, given design means mean value of two random variables. In this case, external force and torque. So here we are dealing with a two-dimensional case. Torque and force are random. And we assume these two random variables follow certain distribution. So in this case, it could be a normal distribution. Then this is a limit state function, so which means here is a safe region and this area is a failure region. And I think you guys are familiar with the Monte Carlo simulation. So if we know the input distribution and if we perform a Monte Carlo simulation at this given design, then we may have this kind of simulation result. So most of the results fall in this safe region, but some of the results here you could see fall in the failure region. So that means that there exists some failure. And prior to failure, like I told you, prior to failure is defined like this: probability that failure occurs. So in this case, g of x is greater than 0. And this probability is evaluated using multidimensional integration like this. In this case, we assume this input PDF distribution information is available. This is a failure domain. Gx is equal to Gx is greater than 0. So in this area, we are integrating this input joint distribution. Then we could obtain product of failure, but again, this is not easy, mathematically easy. And once we obtain product of failure, then again, reliability is 1 minus product of failure. Why this is difficult? Because in general, the limit state function is not linear. So if it is linear, then we could easily obtain this kind of integration. But in most cases, this limit state function is not linear. So which makes the numerical integration very complicated or even impossible. And furthermore, input distributions are generally non-normal. So if it is normal, then the linear function could remain linear after some transformation. But in many cases, input distribution could be non-normal. So because of these two facts, we may have to have some assumptions to obtain this product of failure. So it is required to approximate a multidimensional integration shown here. And the method of reliability analysis, like I told you in the beginning of a lecture, so there are two ways of evaluating reliability. So first one is analytical method or MPP-based method. So form, first order reliability method, SORM, second order reliability method, and the DRM dimension reduction method are all included in this analytical method. So analytical method always find MPP, and at the MPP, a function, limit state function is approximated. So linearly approximated, quadratically approximated, and approximated using dimension reduction method. In the second way, we could use a sampling-based method. So Monte Carlo simulation, so like shown in the previous shaft example, we could use Monte Carlo simulation to evaluate product of failure. Or to reduce the number of Monte Carlo simulation samples, we can use other sampling methods such as importance sampling or Latin cube sampling and so on. There are many sampling strategies to improve efficiency of Monte Carlo simulation. And the method using surrogate models, but we will not focus on the third one. So surrogate model usually combined with sampling-based method because sampling Monte Carlo simulation requires a lot of computation. So usually 1 million or more than 1 million samples are required to accurately perform Monte Carlo simulation. So since we cannot directly use expensive computational model, so we may have to introduce a surrogate model in a sampling-based method. But surrogate model is not main focus of this lecture, so let's skip the third one. So let's see first order reliability method. So from the name, first order reliability method, we can easily see we need to approximate a limit state function at the MPP using a linear function. Again, we need to perform this multidimensional integral. Then the basic idea of form is to ease computational difficulties through simplifying the integrand and approximating the performance function. So these are two steps required. We need first, we need approximate the performance function linearly, and also we need to simplify integrand. Integrand means joint distribution function. So if it is not normal, then we have to have a normal space. So form uses first order Taylor series expansion of performance function. So linearization is used in form. And there could be two reference points for the linearization. So first point is called mean point or design point, which is center of this distribution. And another point is called MPP, which was shown in the motivation slide. So MPP locates on this limit state function. The performance function can be linearized at the mean. So if we linearize performance function at the mean, then this is just a mean-based form. Then by using Taylor series expansion, the performance function or performance function can be linearized like this at mean. So here this is a function of mean. Or the performance function can be linearized at a point on the limit state function. And you know this point is called most probable point, MPP. But before we linearize this performance function or limit state function, even if the performance function is linearized, the probability of failure cannot be estimated if distributions of input random variables are non-normal. So the first step of reliability analysis using form is to transform this non-normal variable into a standard normal variable using Rosenblatt transformation. So this is the first step of form Rosenblatt transformation. So the first step of form is to transform input random variables in the original design space into a standard normal space. Then the X space, which is original space, becomes U space, where all random variables are standard normal variables, so which means mean of 0 and the standard deviation of 1. And again, Rosenblatt transformation can be performed using these. So by equating two CDFs, so CDFs of original variable and the CDFs of standard normal variable. So this works only for independent, statistically independent random variable case. But most cases, standard these variables are independent, so you can directly use this relationship. Then U becomes a function of X, or inversely, X becomes a function of U. And if input distribution is normally distributed like this, so this is notation for normal distribution. X follows normal distribution with mean of mu and the standard deviation of sigma. Then this Rosenblatt transformation becomes this, which is actually a linear transformation. So U is linear function of X. And after transformation, the probability of failure becomes now function of U. So previously, probability of failure becomes probability that G of X is greater than 0. Now in the U space, standard normal space, the probability becomes G of U is greater than 0. And now in U space, all the design variables follows standard normal. So here, lowercase phi means standard normal PDF. So this is given, known. And the important thing here is this Rosenblatt transformation doesn't change the probability of failure estimation. So mathematically, the probability of failure in U space is exactly same as the one in X space. So here you can see the original space. This PDF contour may not be circled in this two-dimensional space because one of the random variable follows non-normal distribution. So in this case, log normal distribution. So it's not symmetric along x2 direction. But in U space, since all the random variables follow normal distribution, standard normal distribution, we could see that this is exact circle. Contour becomes a circle, since the mean value is always the origin and the standard deviation is 1 for two variables, U1 and U2. So the radius is identical. So we're done with Rosenblatt transformation. And then the next step, second step of form, is to linearize the performance function in U space using the first order Taylor series expansion. And again, we could select two different ways of reference points. So one is mean value point, which means origin of the U space, or point on the limit state function, MPP. So depending on which point is used for a reference point, the probability of failure estimation could be different. So if we select mean value point, then the probability failure estimation result could be erroneous, but it requires less computation. But if we select MPP or point on the limit state function, then probability failure estimation could be relatively more accurate than mean value method, but it requires additional computation to find this point. So it searching for the point in the limit state function requires additional computation, like I told you. So that means that approach is more relatively, or in general, more accurate than a method using a mean value point. So by spending more computation, we could obtain more accurate probability failure estimation. So the performance function can be linearized at the mean in U space. So mean in U space means origin of the U space. So here this becomes 0 as in the U space. Then the linearized function at the mean is simplified like this. And then if we have we know this, then we can obtain mean of this linearized function because we know the mean of input, and the mean of the sensitivity is also available. Then mean of this linear function is simply function value at the mean at the origin, and the variance or square of standard deviation is obtained like this. So summation of coefficient square, and the coefficient is gradient or sensitivity at the mean. Then the probability of failure using form at the mean is approximated like this. So probability of failure is defined as probability that failure occurs, and then this is approximated by using linearized function. So G is approximated using linearized function. And using a symmetry of the distribution, this is the same as 1 minus P of this function is less than 0. And since GL follows normal distribution, because U follows normal distribution and GL is a linear combination of a standard normal variable. So GL also follows normal distribution. So we know GL follows normal distribution, then we could obtain this result. So probability of failure can be approximated using this information, where mean is function value at the current design, and the standard deviation is obtained using sensitivity at current design. So these informations are actually used to linearize this function. So by using available information, we could approximate the probability of failure using a mean value method. But again, this mean value method has some error since we are using mean as a reference point. So we may have to have more accurate form than the mean value method. So we want to put this reference point U star on the limit state function. Then we can approximate again using linear function like this, but reference point now is a point on the limit state function. So later we will find this is MPP. Then in a vector form, we could have this. But since this point is on the limit state function, so this value will be always 0. So we will have this linear function. And to minimize the accuracy loss, so it is natural to expand the limit state function at a point that has the highest contribution to the probability integration. So it is important to select this point on the limit state function, and we will select this point which has highest contribution to the probability integration. So which means we want to maximize probability PDF value at the point. So it is preferable to expand the function at a point that has the highest value of the standard normal joint PDF. So that means we need to perform another optimization to obtain this MPP U start point. And again, this point is called MPP, which has the highest probability density of function value on the limit state function. So that means we need to perform this optimization to locate the MPP, which means we need to maximize joint PDF of standard normal U variable while satisfying this. So which means the point must be on the limit state function. So all the points on the limit state function, we want to find the point that has the largest joint PDF value. And this joint PDF function can be expressed using this exponential function. So that means by maximizing this function is correspond to minimize this. So the model for the MPP search can be rewritten as this. Since this minimizing this one is the same as minimizing distance from the origin to the point, so which means L2 norm. So this formulation is equivalent to this formulation, which means we want to minimize this distance from the origin to the limit state function. Then the point is MPP point or most probable point. So here graphically we can see easily. So we want to find the point on the limit state function, and among all the points, we want to find a point that has the shortest distance from the origin to the limit state function. Then that point is called MPP or most probable point, and the distance from the origin to the limit state function is called the reliability index. So we will use this reliability index for probability failure estimation. So it is very important in form how to find this reliability index. So which means how to find this MPP on the limit state function. And mathematically, once we find this MPP, then the probability of failure is simplified as capital phi of minus beta. Beta means reliability index, which is distance from the origin to the point. So once we know the distance, the beta, then probability of failure can be simply written as capital phi. So capital phi means CDF value of the standard normal variable evaluated at minus beta. So regardless of shape of the limit state function, because we are linearizing, the probability of failure is given as a function of reliability index beta. So the procedure of the form at the MPP is briefly summarized like this. So first we need to transform X space to U space by Resemblance transformation, and we need to find MPP in U space, which has the shortest distance from the origin to the limit state function. And once we find MPP, we need to obtain reliability index by measuring the distance. Then the probability of failure is simply given by this. Then this result will be more accurate than mean value based method. So let's summarize the first order reliability method. So to approximate the probability of failure, the linearization of the performance function is used. And for a reference point, we can use mean or MPP. And before linearization, we first use a transformation, so called Resemblance transformation. And the mean value method is more efficient but inaccurate than MPP-based method. So in other words, MPP-based method is more accurate than the mean value method, but more expensive. Expensive means it requires more computations. And then probability of failure is estimated as this, which is a function of reliability index beta. But due to linearization, form contains inevitable error for nonlinear performance function. So which means if the performance function is not that nonlinear, then form shows a relatively accurate result. And let's move to sampling-based reliability analysis. So we saw this is a definition of probability of failure, and this can be rewritten as this. So probability that X, so any point in X space belongs to failure domain, then that means this is a multidimensional integral of indicator function I times joined to PDF. Then using the definition of expected operator, this becomes expected value of indicator function. And the indicator function is defined like this. So if X belongs to failure domain, it is 1. Otherwise, so which means X belongs to safe domain, it is 0. And the failure domain is again defined like this. So G of X is greater than 0, it is failure. Then using a Monte Carlo simulation, the probability of failure can be evaluated like this. So counting the failed samples, so all the failed samples divided by all the Monte Carlo simulations. So this ratio is probability of failure. So we can just count number of samples which fall into failure domain and then divide it by total number of sample, then we could obtain probability of failure. So error in this Monte Carlo simulation here is because of the number of Monte Carlo simulation samples. If we have infinitely many Monte Carlo simulation samples, then there will be no error in the estimating probability of failure. However, the problem is because of the computation, we cannot have infinitely many Monte Carlo simulation samples. So in that case, we can introduce a surrogate model. Then this approach may have some error in surrogate modeling. So from this figure, we can see if we have 10 samples, 100 samples, 1,000 samples, and 100,000 samples, then estimated probability of failure is getting more accurate and accurate as the number of Monte Carlo sample increases. So once we have large number of samples, we can guarantee the estimated reliability by Monte Carlo simulation is reliable. But if the number of samples is not enough, then we cannot guarantee the result is accurate enough. So we can derive percentage error of Monte Carlo simulation for probability of failure estimation, which is given by this. And if we select 95% confidence level, so which means alpha is equal to 0.05, then this value is very close to 2. It is actually 1.96. Then 100 times 1.96 becomes very close to 200. So we can simply say this error is 200 times square root of 1 minus PF divided by n times PF. So from this equation, we can see if we have infinitely large n, then the error goes to 0. Also, if we have very large PF, then this error is also very decreases. So that means, in other words, if we have very small probability of failure estimated, then we need to have a very large number of samples to have the same error level. So this is the end of reliability analysis, and we'll move to reliability-based design optimization. So again, the concept of Rbdo is like this. So deterministic design optimization may have 50% reliability only at the optimum because of the uncertainty of dimensions or material properties, and so on. So this is not safe. So we introduce a safety factor. So if we introduce a safety factor, that means this failure surface or limit state function is moved to inside like this. But even if we select the same safety factor for each function, the amount of this movement will be different depending on the function shape or function type. So we just resort to experience, the designer's experience to select the safety factor. So instead of safety factor approach, these Rbdo approaches use mathematical theory, probability theory. So if we find MPP, then the distance from the design to MPP determines reliability, and this ellipse, or it could be circle if it is in the use space. Ellipse is determined by target reliability. So if we want to have very reliable optimum, then we could increase this target reliability. So by increasing target reliability, we could have a larger ellipse or larger circle. Then that means center of this design circle is far from the limit state or failure surface. So that means the current design, obtained design will be more reliable. So we can control by controlling this target reliability. So the formulation of Rbdo is given like this. So we want to find the D, design vector D, which is mean value of random variable, and to minimize cost function f, which is a function of design variable D and parameter P. Subject to this probabilistic constraint, and to obtain this left-hand side probability, actually we need to perform reliability analysis. So using form or Monte Carlo simulation. Then using form, first order reliability method, we could rewrite Rbdo formulation. So this probabilistic constraint can be simplified if a form is used. So in the form, first we could write target probability of failure as this, using target reliability index beta t. So beta t is given by designer. Then using form, this estimated probability of failure is expressed as this, using estimated reliability index like we studied in the previous slides. Then the constraint, probability constraint becomes capital phi of minus beta, which is left-hand side, is less than or equal to right-hand side, capital phi of minus beta t. And the capital phi, which is CDF, is increasing function. So that means minus beta t is less than minus beta t. So that becomes beta is greater than beta t. So we could rewrite this formulation like this, and this becomes deterministic design optimization. Or sometimes inverse reliability analysis is more efficient than reliability analysis for design optimization. So reliability analysis, we performed this optimization. We want to minimize distance from the origin to the point subject to this on all the points on the limit state function. But inverse reliability analysis, we are changing this objective function and constraint function. So we want to maximize performance function subject to this. So which means on this circle, we want to find the point which maximizes the performance function. And this maximum point is belonging to this safe design. Then that means this design is safe. And if this point belongs to this failure domain, then that means the current design is a failure. So for performing Rbdo, we may not have we may not obtain this reliability analysis result. So instead, we could perform inverse reliability analysis. So the inverse reliability analysis result is just to check whether the given design is safe or not. We don't need to obtain accurate reliability analysis result. So in most cases, inverse reliability analysis are more computationally efficient because the size of MPP search space is affect efficiency of MPP search. So that means if the current design is far from this limit state function, reliability analysis requires more computation to locate MPP on this limit state function. But inverse reliability analysis always finds MPP on this hypersphere with target reliability index beta t. So in many cases, if current design is far from the limit state function, inverse reliability analysis is more efficient. So usually we use inverse reliability analysis for Rbdo. In that case, optimization formulation is written like this: minimize cost function while satisfying the function value at MPP is less than or equal to 0. And this MPP is obtained from this inverse reliability analysis. And the sensitivity for performing design optimization, we need the sensitivity, and the sensitivity of this probability constraint is easily obtained using sensitivity at the point. So this is doesn't require additional computation for obtaining sensitivity. And using sampling-based Rbdo, the probability of failure is estimated like this. Then the sensitivity of this probability of failure obtained by Monte Carlo simulation is also obtained like this analytically. And one Monte Carlo simulation, by using one Monte Carlo simulation, we can obtain a probability of failure estimation and its sensitivity evaluation result. So by using this result, we could also rewrite Rbdo formulation. So this is end of the concept of Rbdo, and I will give you some two engineering example how this Rbdo works. So first example is M1A1 tank Rbdo, which is shown here. So we want to design the shape of this Rbdo, and there are 8 design variables, so which means intersection. There are 4 intersections, and height and width of this each intersections are design variables. So from D1, D2 to D7, D8, by changing the height and width of this intersection, we could have infinitely many design of this road arm. And objective is weight. So we want to minimize weight of this road arm. And again, constraint is probabilistic constraint. So 2.275%, which means 2 sigma design. So this is target probability of failure. And there are 13 constraints. So here, constraint is fatigue life. So fatigue life, L of X is correct initiation fatigue life. So to obtain this point, actually we need to perform fatigue analysis. And we select candidate point by performing this durability analysis. And the correct initiation target fatigue life is 5 driving years. So the correct initiation fatigue life should be larger than this 5 driving years with 1 minus 2.275% reliability. That's the objective of this formulation. And this shows a parameterization of the each intersection. So intersection is controlled by width and height. So by changing width and height, simultaneously, we could obtain various cross-section area. And also, we use correlated material property for this road arm. Yeah, and this shows parameterization using hypermorph, which is in Altair software. So this green ball means control point. So by changing the location of this green ball, we could obtain this kind of expansion or this kind of contraction. And to perform this example, there are many softwares used, like Pro-E for solid modeling and dynamic analysis, fatigue durability analysis, and the design sensitivity and Rbdo codes developed by myself and my seniors. And this is DRAW is durability analysis code. So combining all these softwares to evaluate the fatigue life and to perform reliability analysis and design optimization, then we could obtain this kind of results. So initially, the weight is this, and this is initial design. And if we perform deterministic optimum, then we could reduce this weight by like 10%. But again, this design, deterministic optimum design, could have 50% reliability only. So we could perform Rbdo using two ways, MPP-based Rbdo, so form, and sampling-based Rbdo using Monte Carlo simulation. Then we can see almost the same results obtained using each method. So by increasing the deterministic optimum result certain amount, we could satisfy target reliability, which is 97.7%. So I'm not sure whether you can see. So by comparing these two results, we can see this part is thickened and this part is narrowed. So we could see the design is changed. And the second example is heat cooling flange example. So here, fluid is passing through this cooling flange, and the cooling air is flow this direction. And this is FE model of this cooling flange, and this is design parameterization. So there are several design variables. Again, we want to minimize the volume of this cooling flange while satisfying this probabilistic constraint. So we want to satisfy this cooling performance is, and the target prior to failure is 5%. Then there are, we can compare three designs. So original design and deterministic optimum and Rbdo optimum. So here you can see deterministic optimum, it reduced the volume a lot, but the prior to failure is almost 50%. So half of them are failed due to uncertainty. But if we increase this volume a little bit, like this much, then we could satisfy the prior to failure like this. So here, this prior to failure is different from target because we are using a first order reliability method, which involves a linearization error. So here we can see 5.5% error, which is a little bit different from 5% target prior to failure. And you could see initial design, deterministic optimum design, and this is Rbdo optimum design. Yeah, this is it for my lecture. And if you have any question, please let me know.
Thanks, Dr. Lee. The floor is open for questions. You can ask or you can type in the chat window.
PPT. So one question from the chatting log. So can you share the PPT slides or yesterday? So at least my PPT file can be shared. So I will send this PDF file to the host so that a host can share my slides.
Okay.
Sure. The videos themselves will be shared. They will be put up on sharing. So I mean, even better than slides, you can watch the whole video again. I mean, if you want.
Okay, so yeah, then I don't need to send that. Yeah. But some attendants may prefer slides only, so without my voice.
Sure. I'll put it up somewhere. If I'll then ask everyone. I'll then ask everyone to send the slides, and then I'll put them up somewhere.
Yeah. Or attendees can directly contact me to request these slides.
Or to ask more questions, or maybe some research initiative.
Okay.
Yeah, sure. We'll provide the slides. So one of them, okay, what is the difference between reliability optimization and meta-heuristic optimization?
Meta-heuristic?
Correct. That is the question.
Oh,
What
yes.
is
So here, meta-heuristic optimization is, I'm not sure whether my understanding is correct or not. Meta-heuristic is just one way of optimization, which does not use sensitivity. Is that correct? Yeah, then we could use reliability, we could perform reliability optimization using meta-heuristic method, such as generic algorithm. So as meta-heuristic optimization is one way of optimizer. So this is a type of optimizer, and reliability optimization is different from optimizer. So reliability optimization can be used in by using any optimizer. So it is different. Yeah, there are different optimizers. So how can I say? So one way of optimizing certain problem is like meta-heuristic approach, meta-heuristic optimization method, which is different from gradient-based optimization method. So here, a form is usually based on gradient-based optimization. So in that sense, they are different. Any other questions?
So Professor Lee, I had a question. So
Yes.
in your slides, you mentioned that the safety factor based approach versus the probability based approach.
Yes.
Now, the safety factor based approach depends on experience and it's more ad hoc or it's more arbitrary, right?
Yeah.
Whereas the probability based approach is more rooted in mathematics and there's a procedure for it. Now,
Yes.
when you calculate sensitivities, is it procedure to check what happens or how the sensitivities are when you change the distribution? For example, if you choose a non-Gaussian distribution, or is that part of these kinds of studies? Because the distributions are not always Gaussian from what I understand. I don't work in these kinds of areas, so I'm just...
Yeah, so distribution, usually we just assume distributions are Gaussian or normal distribution. So in that case, many problems are solved very easily. But even if they are not Gaussian distribution or normal distribution, if we use just a Rosenblatt transformation, we can make all the inputs Gaussian. But result, yeah. But assuming the non-normal input variables as normal distribution, then we could obtain different result because we had a wrong assumption, right?
Right, right.
Yeah, but the design itself is not that different. But the calculated product failure could be very different because it is very sensitive to the design, the location of design. Yeah. So correct input estimation is very important.
Now, is the industry accepting this reliability-based approach? Because they follow the safety factor-based approach quite a bit. But
yeah, I
is it
understand.
being accepted into the mainstream now?
Hyundai Motors. Do you know Hyundai Motors? Yeah.
Mm-hmm. Yeah.
Hyundai Motors accepted this kind of idea. So I had a project with Hyundai Motors. But usually the heavy industry, such as shipbuilding industry, they don't accept this kind of approach very well because they have very well established safety factor approach. They don't want to change this approach because it causes a lot of money. And if the design fails, they have to spend more money as a penalty. So they don't want to change the design approach. But
Right.
like I showed you, just the engine design for a part of the ship, then they want to change the design approach. For a small part of the ship, they want to accept this kind of approach, but ship itself, they don't want to change it.
Yes.
Oops.
Any other questions? Please type in the chat windows.
If you guys don't have any question right now, I will distribute this PPT slides, and once you study this PPT and you have a question, just let me know by email. And it is always welcome to receive an email.
Yeah, that will also be very good, actually. Thank you for the offer.
So are we closing? No.
Just give it a minute or so to see
Yeah.
if anybody else has questions. Otherwise, then we can close. So the question is, any reference book for Rbdo? Any recommendations?
Yeah, theory. Just hold on, please. Can you guys see this? Yeah. Title is Probability, Reliability, and Statistical Method in Engineering Design. So this is, I use this as a reference book for my class, Rbdo class, written by Halda and Mahadevan.
Oh, Mahadevan. Okay.
Yeah.
The Vanderbilt professor.
Yeah, Vanderbilt.
Okay. Okay. Statistical methods in engineering design.
Yeah, probability, reliability, and the statistical method
Statistical
in
methods in
engineering design. Yeah.
I put it in the chat. I got some keywords so you can search.
Yeah. This is just the starting point of studying Rbdo because it is written a while ago, so it doesn't include a recent method, but it is a good book to start studying Rbdo.
Where is the field now? I'm assuming data-driven methods have infiltrated this field as well. So where is the field now with emphasis on AI and ML everywhere? How is that impacting this kind of area?
Oh, so I wrote one paper for sampling-based Rbdo, and sampling-based Rbdo requires a lot of samples. And to accelerate the computation, I introduced a deep neural network. And then by learning in advance this kind of reliability estimation using deep neural network, we could obtain the estimated result very fast. So we could use this AI even in a reliability analysis method.
We have another question. Do meta-heuristic methods provide any advantage in Rbdo?
Like I told you, Rbdo can be directly combined with meta-heuristic approach. So it's not separate. We could combine them. And if we combine them, what could be advantage? So especially in sampling-based Rbdo, if we have a surrogate model, then this meta-heuristic method, which requires a lot of computation, can be used for Rbdo. Then the advantage is advantage of meta-heuristic approach is it finds global optimum very well. So that's the advantage of meta-heuristic method, not advantage of meta-heuristic method combined for Rbdo. So I'm not sure a specific advantage for meta-heuristic method combined with Rbdo. So anyway, there is no reason not to use meta-heuristic approach in Rbdo. So if you want, you can combine this meta-heuristic approach for Rbdo. But usually design optimization guy want to reduce the number of computation, but meta-heuristic method requires a lot of computation. So that's the disadvantage of meta-heuristic method.
Any other questions? So, Professor Lee, is it okay to share your email ID with the audience in case they have any questions?
Yeah, sure. Actually,
Okay.
the last slides includes my email address. Yeah.
Okay,
So if
excellent.
distribute these slides, then attendants can anytime attendants can send email to me regarding this lecture material. Yeah.
Okay. Thank you so much.
Yeah. Thank you.
Yeah, thank you. And we'll close the session. Thank you very much for your talk.
Thank you, Professor
And,
Lee. Thanks a lot.
Yeah.
and being
Thank
a
you for
part of
having
this
me.
workshop. Yeah. Thank you. Bye.
Yeah. Bye.
Should I close?